So, hello everyone, I'm Mike Cook. I currently work at Queen Mary, where I did this work with Simon Colton and Jeremy Gao. And we also collaborated with Julian Smith, who works at WPI over in Massachusetts. And the title is very, very fancy looking and sounding, but what it basically boils down to is this. We wanted to build better ways for people to understand procedural generators. And so today, I'm going to talk to you about a couple of concepts we came up with, a couple of analytical techniques that help people think differently about procedural generators. So this is the interaction loop for someone working with a PCG system, okay? And this user may not have made the procedural generator. They might have downloaded it from the internet. They might work in a team. They were given it maybe. Maybe they're like a kid playing with an installation in a museum. And the way this works is this algorithm can be made to produce things, to produce content, which the person can look at. And they can fiddle with the inputs to the system, tweak buttons and things, and change variables in the code maybe, and that affects the way the procedural generator behaves. And this interaction loop has two interesting features to it, which relate to what many of you might have been sick of hearing of, but I only really got into recently, which is Norman's ideas about interactions with systems. So one of them is what we call the gulf of evaluation, and that's this half of the loop. And this is about how easy is it for the user to figure out, like to get a sense of what the system is actually doing, right? So how easy is it for them to work out by looking at the content, for instance, by looking at what the system does, how well do they understand what is going on inside the system, right? And a lot of existing research into procedural content generation focuses on this problem, right? So things like expressive range analysis, which was Julian Smith's work from back in 2010, great paper, very influential. And our more recent work on a tool called Danesh, which was designed to automate some of these processes and do some fancy stuff on top. These are focusing on how can we help the user understand what their generator is doing. So it's visualizations, it's interactions, things like that. It's not interactions. It's not interactions. It's just visualizations. Now the other half of this problem is what Norman calls the gulf of execution. So the evaluation problem is what is this system doing? And then if you decide you want to change what the system's doing for some reason, maybe it's because it's not doing what you want, or maybe you're just exploring, the problem you're faced with then is, do I know how I can affect a particular change? Do I know how I can achieve a goal that I have about changing the way the system behaves, right? And this sort of aspect of the problem is less often looked at in PCG, for PCG at the very least. So the reason why this problem is so thorny is because when we think about procedural generators, we have this code that does something, this code that generates stuff that has these variables and these controllers and stuff. But then the way that we evaluate the output is very different. It's more about the qualities that the finished artifact has, right? So if we're generating Mario levels, for instance, you might be interested in things like how fun is the level or how difficult is the level. These are very, very funny qualities for something to have. And they don't relate to some variable that controls how often a Goomba spawns on a floor tile. It might have an influence on it, but it's not like a one-to-one mapping often, right? And sometimes these are abstract. These are like mathematical functions that manipulate noise and things like that. So there's a real disconnect between what we put in and what we get out. So a good way to think about this problem is to think about the shower in your hotel room or your home right now. So the classic problem with this is that you have a little control that affects how hot the water is, and in an ideal world, as you turned this control, you would get a linear response from it, and it would evenly affect the temperature of the water, and you would be able to tell what was going to happen before you did it, right? That's the gulf of execution being narrow. But in reality, as we know, what happens is as you turn this control, it suddenly gets hot very quickly, then it gets cold again for no reason, or the speed at which it gets hot, like the rate of heating up, changes. And that's what makes showers unpleasant. And this is actually even worse in my home in Germany right now. We have two controls. One is for temperature and one is for pressure. And now it's even weirder because now the behavior of one of these controls is affected by the other one. So when the water's hot, I might get this effect from the water pressure control. And then if I make the water colder, suddenly the water pressure is behaving differently because the pipes are expanding and contracting, or other things that was just broken and really old, which is probably the actual case. So basically, these controls aren't behaving as we expect them to behave, right? And that's a problem. So the thing that we propose in the paper, the first thing that we propose is this notion of smoothness. And I'm going to talk to you about it now, mainly with an example of procedural generator. But the basic basic premise with the shower example is that we have some controller, some input to a procedural generator that we want to analyze. We want to understand why is this behaving the way it's behaving, or how is it behaving in any case, right? And then we have some way of evaluating, like, something that it is affecting that we want to measure. So in this case, it's water temperature, which is very obvious, but in our procedural generator, it might be something more complicated. Now, before I talked about things like the fun of a platformer level. For the examples that we're talking about automating this process. So you can't measure fun with a bit of Python code. And so typically these metrics will be slightly different. There'll be things like enemy density, or we'll have a look at some examples of like little dungeons later on. But the important thing is that we have a controller, and we have something that we think the controller affects, right? So in our case, we're going to call them parameters and metrics. So the parameters are the inputs to the generator, and the metrics are what we're measuring. So the way that we perform what we call a smoothness analysis is this. We turn the parameter to a certain value, so usually it's like regular intervals along its range, so maybe 10% or 20%, 30%, all the way up to its max value. And then for each one of these parameter values, we run the generator a bunch of times and take a big sample of outputs. So we generate 500 Mario levels, and then we measure this metric for each one, and we plot the average score on this graph. So it's very, very simple. Set one parameter, measure this feature across a large sample, and plot it. And when you do all of them, you end up with something that looks a bit like this. And this is what we call the smoothness of this parameter with respect to this metric, right? Now, in an ideal world, remember the shower, what we would expect is, and this is obviously very impractical because we just made up this metric, but what we would expect in an ideal world is, as I change this input to my procedural generator, this feature that I'm interested in magically, smoothly changes, right? And the reason why that's important is because if I'm a user and I'm trying to change something in my generator and I make a small tweak, my guess about the next tweak's effect is based on what I've seen happen in the past, right? So if I see this jump here, then the next time I make a similar change to the parameter, I expect a similar kind of strength of effect. What we see in practice, and this is like basically a real result that we got when we analyzed one of the generators that we had, is that its behavior is really unpredictable. And what that means is that if my first change is this little chunk here, and then I think, no, that's nice, but I'd like it kind of twice as high, and I make another small change, suddenly I'm in completely different territory. And it's not just that that's unexpected, it's that depending on the way you're changing these parameters, it's actually extremely hard to find a particular thing. If you're trying to get this metric value to average out here, this is so steep that it's extremely difficult to figure out which bit of the range is interesting and relevant to you. And this is an example just pulled from the paper of a smoothness analysis. And basically, when we were doing all this work, I got to this point and I was like, this is actually just really useful as it is. Many of us here are kind of people who work with PCG a lot. We could use this to analyze the behavior of certain aspects of our systems. But it's not just an esoteric analysis tool. We can also use it to build smarter tools for everyone to use, right? So in a tool for, like Unity, you're changing your procedural generator, or maybe you're using Ganesh, you're one of the 3 people in the world who, I love you all, if you're any of you in the room. So normally you're in control of this parameter. You're sliding a value and you're changing a parameter. And what we do to fix this steep problem is that we've tweaked Ganesh so that it lies to you, and you think you're in control of this parameter. What you're actually doing is you're controlling something else entirely. So what I mean by that is that the slider that used to control a parameter score, in our Ganesh interface, we replace it with a fake slider. It basically looks exactly the same. And what we do is, when the user sets a value for this parameter, what they're actually doing is they're telling us, because we've smoothed the variable, they're telling us what the metric they want, really. That's what they're really telling us, is that they're telling us, where exactly do they want this metric to end up. And so what we do is it's extremely simple. We just do a reverse lookup on this smoothness graph that we've produced. And we find out, okay, they wanted this to be, a mid-range value. Where is the mid-range effect on this actual parameter scale? And then the real slider is happening behind the scenes, and Ganesh is silently editing the real parameters under the surface. So let me show you what the actual impact that has. So This is my famously ugly cellular automata dungeon generator that I use in all of my Daesh talks. So the orange stuff is empty space and the brown stuff is walls. And these are 5 samples as we slowly increase this parameter. And you don't need to know what the parameter does, because that's the whole point of this exercise, but it does something, right? And you can see that as we increase, the amount of walls become more until there's basically no space left, right? You can see here it's basically fully empty. This is pretty much unusable unless your game is about digging, and the last ones are just absolutely unusable. This is what a smoothed version of this looks like. And I'm going to take you through these like zoomed in a bit. So when you're at 25% of this parameter's value that we don't know what it is, this looks pretty good actually. This is usable. This is the before version. And the after version also looks pretty usable. But 50% across, this is now not good anymore, because for that parameter, if you remember that curve that we were looking at earlier, this parameter has now done something horrible to our generator, and it's just not what we want anymore. But when we smooth it with respect to the density of the level, you can see this is actually reusable still, because it's about 50% dense. We found a version for this, a value for this parameter, a secret value, that achieves this middle ground result. And when you look at 75%, it's the same thing again. This is now completely, there is no game really that would use this, and they certainly wouldn't procedurally generate it. But that one on the right, it's got some islands, like it's not perfect, but it is pretty much like a slightly more than halfway, a more extreme result. And what we've done effectively here is, from the user's perspective, we've transformed this into a linear relationship. So, that's smoothness. The problem with procedural generators is that there's never just one thing to control, just like my shower in Germany. And they have loads of them, loads of inputs. And as we were discussing before, often these inputs interfere with one another. So another thing that we propose in the paper, which I'm not going to go into in loads of detail in this talk, because it's a kind of a straightforward extension of smoothness. But the thing that we go into in more detail in the paper is this thing that we call codependence. And what codependence lets you do is it lets you see how the smoothness of a parameter changes based on the value of a second parameter, right? So it effectively adds kind of another axis. If you imagine that this was 3D and not very bad, this would be, this allows you to see, as we change the value of this second parameter, how does the smoothness of this parameter change? How does the behavior? So as I change the temperature of the water, how does the water pressure change? And the way we do this is extremely simple. You have this second parameter that we're calling Q, and you change it just as we did earlier in the smoothness example. You change it at regular intervals, and every time you pick a new interval, you do a full smoothness analysis of your first parameter P. And you plot them all together. I mean, I plotted them here on this one graph to give you an example. So you can see that as I change Q, the smoothness behavior of P is changing, right? It's getting less steep. And if you put this through some LaTeX magic, you end up with, actually, we can plot this as like a really beautiful 3D shape. And this is like the 2D, this is like 3 slices through it. And what you can see here in this example, for instance, is that this parameter generally does not change the smoothness of this one. It's pretty much the same. Like you can see here, the gradients are very similar. This red and blue line are very similar, except when the value gets very low. When this parameter gets very low, suddenly you see a massive change in the behavior of this parameter. In fact, like the curve inverts. And so you can see there is dependency between these two parameters with respect to this other metric. Right? And so codependence is also like an excuse to draw really cool pictures. But again, we can build smarter tools with this. So this is Danish's sliders again. And so now imagine that as a user is changing one of these parameters, we're doing a codependency analysis in the background. And these parameters are being highlighted to warn you, okay, this parameter, now it behaves differently. Like, I'm not going to tell you how, that's not important because, we want to keep this simple, but it's not going to behave the way you thought. And maybe you click a button that says, okay, smooth this parameter for me again, re-smooth it so it's going to behave in a way that I expect. So, just this one last slide to point out that the things that I've shown you here and the things in the paper are like 2-dimensional and 3-dimensional, and that's because it's kind of designed for like a human analysis so that we can see it. But there's no reason why we couldn't build even cooler automated systems that do smoothness with like six metrics at once, or multiple parameters in n-dimensional space. Like, there's lots of stuff that this can be applied to, and we're hoping to look at that in the future. So, one last slide before close. The reason why I think this is important is because it supports procedural generation as a creative exercise, right? And because it's giving people control over what they're doing and more understanding. So when you watch DEC talks about people joking about procedural generation, even people that love it, they talk about it's unpredictable, I don't have control, all of these things, even people who adore it. And this is helping, I think. These kinds of things help. And in particular, it helps because we're trying to aim for things that are domain agnostic. That's expressive range analysis' great strength. It doesn't care what you're generating. And these ideas are hoping to go in that direction as well, so we can start to share ideas across areas and talk more generally about what we're doing. All right, sorry that was a bit breathless. Here are my lovely co-authors on Twitter. I'm also on Twitter, but I'm less coherent. Dinesh has not been updated for a long time, but if you are interested, there is more information on that website. Okay, thanks very much. Okay, cool. I've got some questions. Vanessa, I think you have some.
I was wondering, Ahmed, do you handle multimodal functions? So what if it doesn't just go up, but it goes down?
Yeah, so in the paper we mentioned about monotonicity. So if this function is not always increasing, you have problems. The way we anticipate dealing with that is by slicing it at the turning points of the functions, and then in the case of applications to Dinesh, you'd have to tell the user, okay, once you go past this point, I can't predict what's going to happen next necessarily, or I can't necessarily smooth it, but you'd have individually smoothed segments, which is a little inelegant. But we haven't, I mean, they definitely do exist. I think they won't be uncommon, but we haven't come across too many examples of that yet. But it is yeah.
It's a target value or something, and you have a sweet spot.
Right, yeah. Do you want to handle it? Yes.
No. One of the problems or one of the things you said is that you have to analyze what the output is, and you said you did it manually. You're going to analyze whatever 100 points or runs that you have in the game, and then plot it out, etc. When you start increasing more dimensions in terms of parameters, then your scope increases exponentially. How do you manage to create your smooth functions when you have 10 parameters?
Yeah, so at the moment, and I think this is a necessary feature of the way that we've done this, is that smoothing is done with respect to one metric, and in particular, and smoothing is done one parameter at a time as well. You can kind of cache these smoothness analyses, so you can reuse them in some ways, but we're hoping that if we can get it fast enough, it won't matter, because as soon as you click on a parameter, we've smoothed it for you. That's the hope. It is an issue, but I think for the use cases we're interested in, the way I imagine this being used is you're a programmer, you've built a PCG system for someone else to use, and they're this parameter is weird. And so you use this analysis to be why is it weird, where is it weird, when is it weird, and then you fix the tool in a different way for them. So that's how I originally envisaged it, not as a live thing, which we ended up doing. But yeah, I mean, it would become, otherwise it would become massive. Yeah, there would be definite problems. Yeah.
Thank you.
So you found that's great work as per usual, but when you start by doing an average over several generation, and a lot of systems are non-deterministic, and we're interested in standard deviation and median, so don't you think that at some stage, to guarantee a good generation for the user that corresponds to what is selected after smoothing, you would have to go through batch generation and filtering after the fact?
Yeah, it is an issue. It's also an issue with some of the other stuff that you may have seen in Dinesh in the past, where we can optimize your parameter space, but you pick a point and we don't tell you how big or small the variance is around that point. And that needs further study to see how that could be mitigated. Here it's a bigger problem because we're actually as you say, building functions around it. One of the things that we ended up not incorporating, but one of the things you can kind of see here is that here we were trying to capture standard deviations away from the mean as well. So we were smoothing, but also showing you that here there's much less variation than there is here. But yeah, currently that's not something that's captured with, for instance, our automated smoothing. But it's clearly there to be worked in the future for sure. Yeah, that's great.
Another person to set up on
Yes. Simon.
Yeah.
David.
So a lot of mixing games are kind of threshold and not smooth and continuous. So for example, let's say you have 50 hit points and I do 49 damage with my shot. You take 2 hits to kill. But if I move my damage up by 2%, now it takes half as long to kill you. So how do you deal with that sort of, how do you smooth that sort of thing?
So I think in this point we're kind of aggressively smoothing because we're like we don't care that it is thresholdy. We know that you want to pretend that it isn't, or that's like the claim in the automatic case at least. It's a difficult one. I'd have to think about it. Like it's quite a difficult use case. But yeah, I mean I agree. Like we're making this is an aggressive approach for sure. Okay, and we'll chat in the coffee break maybe so that we can move on. Okay. Yeah. Next up, thank you Mike for that excellent talk. Next up is. I have signed it. I'll get Simon to sign it as well later. Okay. But for now, Simon, please take it away. Are you? Oh, yes, you are.
Yeah. Yes. So hello, welcome to my presentation about our paper. So my name is Simon Seibt. I'm the second author of the paper, and I'm a research assistant at the Institute of Technology in Nuremberg. In our paper, we present a PCG tool for indoor levels, which we call level graph. Yeah. So, but what exactly is level graph? And how does our tool work? So let's take a look at the next slide. Yes, so level graph is our approach for semi-automatic generation of a wide variety of 2D and 3D indoor levels, so for corridor and room systems. Yes, and our approach implements an iterative procedural generation pipeline with 4 main pipeline stages. So I will explain these stages in more detail on the next slides. Yes, and our pipeline is based on the graph data structure. So the resulting graph represents the abstract model of a static indoor level. So vertices are position of rooms and edges are hallways. Yes, and the core algorithm of our approach is built on the computation of an extended minimal spanning tree, which can be controlled by a set of innovative vertex and edge parameters. Okay, so let's take a closer look at our pipeline. Yes, so here we can see an overview of the complete pipeline, which is represented as a modified UML activity diagram. So the 4 main pipeline stages are shown in different colors. So therefore a so-called base graph is generated first, so it's the green box. So since the MST is computed, after that the level graph structure is generated, so it's the blue box. And the last step, the geometric representation of the level is constructed. And if we take a closer look at the 4 stages, we can see that the base graph stage, the MST stage, and the level graph stage have 2 substeps. So, and the last stage has only 1 substep. Yes, so these substeps are still nameless in this diagram, and I will describe the substeps in more detail on the following slides. Yes, and in addition, you can see that each substep can be repeated as often as you like. So this is represented by the decision symbols in the diagram. Yes, and after each topic, the current result can also be modified manually by the user. Okay, now I will explain the individual stages and the substeps in more detail. Yes, but before we start with the first stage, a high mesh must be defined in our pipeline. As I've already explained, we generate indoor levels with our pipeline. So the generation takes place inside a user-defined high mesh. So for example, a high mesh can be a simple bounding box to generate, for example, rectangular mazes. And in order to generate only 2D mazes, a bounding box with low depth can be created, as you can see on the left side here. Yes, or a high mesh can be, for example, a complex 3D model. For example, a mountain that should contain a mine level later. Yes, okay, now we can start generating the base graph, which is the first stage. But what is the base graph? The base graph is used to describe the final abstract structure of the level, where vertices are later mapped to rooms and edges to corridors. So the base graph does not represent the final level structure. It is randomly connected and contains just all possible candidate edges for the MST generation. Yes, so we can see that the base graph has 2 substeps. So first, we generate the vertices and then the edges. Okay, but how does the vertex generation work? To generate vertices, the high mesh is overlaid with an axis-aligned 3D grid. Yes, and we implement a process which randomly instantiates vertices within the grid cells. Yes, so on the right side of the slide you can see a simple generation example for a 2D maze. So for the generation we can set the following parameters. So we can set the resolution of the grid, the probability for the instantiation of a vertex in a grid cell, and we can also set the maximum vertex distance to a cell center. So as you can see in the small example here. Yes, and the number range for multiple vertices per cell. And we can also set the maximum count of retries. So if a vertex is created, for example, outside of the high mesh or intersects the high mesh. So this parameter can be used to control the vertex density and irregularity. Yeah, so after the nodes have been generated, we can now construct the edges. So the construction is based on the grow process, which starts from an imperative seed vertex and generates a fully connected graph by using a graph-first traversal on local nearest neighbor vertex sets. Okay, so we determine a new local nearest neighbor vertex sets for each currently selected vertex. Yes, and this generation process is ruled by the following parameters. So the minimal and maximal size for the nearest neighbor set, and we can also define a vertex degree range. So this range allows us to define how many edges a vertex has. So we can set the minimum, maximum number of edges. Yes, and by using the nearest neighbor vertex set, these edges can then be created. Okay, and we can also set the minimal and maximal angel between incident edges. So on the right side, we can see a simple example. So where the minimal and maximal angels were set to 90 degrees. So this creates only, for example, rectangular mazes. Yes, and the last parameter is used for 3D levels, so to regulate the steepness of corridors. Yes, okay, so after we've generated the base graph, we can now compute the MST. At this stage, we have, again, two sub-steps, as we can see here. So first, our base graph is weighted, and then the MST is computed. Okay, but why is the base graph weighted? The base graph, the weighting is performed because the MST algorithm requires weighted edges and compute a tree with minimum total weights. So in our pipeline, we interpret at weight as violations of certain design preferences. So therefore, violations can be geometric intersections and unsatisfied parameter settings. Okay, so what are geometric intersections? A geometric intersection exists if an edge of the base graph intersects a vertex, the high mesh, or another edge. Yes, and there's also a violation if an edge length is greater than the maximally allowed relative deviation from the corresponding average value. So edges or better corridors which are too long can be removed by the MST. Yes, and already during the base graph generation, so one step before, the number of violations can also be tried to be minimized. At first, only edges are inserted into the base graph, which keeps the parameter settings of the edge grow process. And if the number of constructed edges is less than the required degree minimum, edges with less violations are selected. Yes, so how does the calculation of the edge weights work now? So let's have a look at the next slide. Yes, so the final weights are calculated using the following linear combination formula. So W is the weight for the base graph edge I, and F is the user-defined penalty factor for a violation type T. So this factor allows the user to prefer violations. Yes, and S is the corresponding selection function for a violation, which can be 0 or 1. Yes, and after weighting the edges, we can now generate the MST. In our pipeline, we are using the algorithm of Prim to compute the MST. Yes, and the resulting graph can then be interpreted as a level skeleton with a minimal number of violations of design preferences. So here in the example, the green edges are now the MST, for example. Okay, so after we have calculated the MST, we can now enter the next stage, so the level graph stage. In this stage, we have two sub-steps again, so which represent, in this stage, design options. So first we can form cycles, and then we can clean the graph under certain conditions. As a result of this stage, we get the final level graph structure. Yes, and the final level graph structure can be used to generate the final geometric representation, or it can be exported and imported to another pipeline run, which, for example, will have different parameter settings. So this process is represented by the red boxes here, and we call this process graph merging. So a final level graph structure can merge by individual separate generated level graphs with different parameter settings. Okay, so now let's have a closer look at the two sub-steps of the level graph stage. Okay, so why do we need the cycle forming design option? So because the MST has the properties that it's a cycle-free graph, and in practice, dungeon-like game worlds often allow round tours. So we have added a design option to our pipeline that allows us to add cycle-forming edges to this graph again. So, okay, so how does it work? A user-defined percentage of removed base graph edges is set for reiteration. Yes, and there are also two conditions to perform this process in a controlled manner. So first, edges with lower weights are selected with higher priority, and second, edges with comparable weights can be picked randomly. Okay, now let's have a look at the graph cleaning option. So why do we need this substep? Because the resulting cycle graph can still contain edges with violations. So we have added another design option to our pipeline that allows us to remove violating edges and associated incident vertices. So, okay, how is this design option implemented? So we search for vertices belonging to an edge I, whose weight is 0, and another edge j, whose weight is greater than 0. Yes, and if a subgraph spanned by edge j contains less than a user-defined number of non-violating edges, all vertices and edges, including j, are deleted. As you can see on the right example here, here's the number of the here's the user-defined number is 2, and the subgraph has only one non-violating edge. So the complete subgraph is deleted. Okay, now we have generated our final level graph structure. And in the last stage, the final indoor level is generated. Yes, so for this, the level graph structure is converted to a geometric representation. So how was this step implemented? Yes, for the conversion, a set of pre-modeled 3D components is required. Okay, but which 3D components are needed exactly? So we need rooms, dead ends, corridors, doors, and gap fillers. Yes, and these components can be used as follows. So vertices of the level graph are mapped to rooms, but if the degree value of a vertex is only 1, for example, then the vertex can be also mapped to a dead end. Yes, and the graph edges are mapped to horizontal or vertical corridors, so this depends on the steepness. Yes, and in addition, we use GSG operations to trim corridor components which are too long for us. Yes, and the components door and gap fillers are left here, are still left, yes. So these are used to join corridors and rooms. Okay, and here we also use GSG operations to cut out the room entrances. Okay, so that was our high-level concept of our PCG pipeline. Finally, I would like to show some first results. Yes, so here we can see a 2D maze and a 3D maze. So the 2D maze has about 50 nodes and about 60 edges. Yes, and the 3D maze corresponds to a 3D version of our 2D maze. So it has much more nodes and edges. Yes, and the complete runtime until we have generated the level graph structure with our pipeline is 77 milliseconds for the 2D maze and around 600 milliseconds for 3D maze. So these runtimes are needed to generate the base graph, the MST, and the final level graph structure. So the first 3 stages in our pipeline. Yes, and as we can see, the level graph structure uses very little memory. And the last point here. Yes, and here we can see a dungeon level, which is represented a more practical level design example. It is shown, it shows a mine in a fantasy setting and it's located inside a mountain. So the black area here was used to define the high mesh. Yes, and the gray object here is a manual placed 3D arena object that was also taken into account during the base graph generation. Yes, so for this level, the runtime was still far below 1 second, and the memory usage is still low, as we can see. Yes, and our last example is a space station. As you can see on the slide, we used simple high mesh geometries, and the final level graph structure of the space station was merged by 6 individual separate generated level graphs with different parameter settings. Yes, and for this level, the complete runtime was about 44 seconds, and the graph structure requires about 40 megabytes. Yes, and here you see the geometric representation of the space station. So the space station has over 1,000 rooms and over 2,000 corridors, so it's a really big level. Yes, and so what is our conclusion so far? Yes, so our first results have shown that our generation pipeline proves to be basically suitable for practical use and allows the efficient creation of complex indoor levels. Yes, and the runtime are small enough to implement our iterative level design approach, and the corresponding data structure require little memory resources. Yes, our generation pipeline was implemented as a plugin for the Unity 3D game engine. So the current version of the graphical user interface is on the development stage of a scientific prototype. So here it's absolutely necessary to design an interface for non-experts. So for example, graph parameters should be mapped to simpler terms or combined into easily understandable meta parameters. In addition, predefined parameter sets could be introduced, for example, to better support the designer vision. Yes, so, thanks.
All right, questions?
Yep.
Could you give me an example of one of the design constraints that you were having to work with? You mentioned that in the earlier cycles, I wasn't quite clear on what they were.
Earlier cycles?
In the earlier cycles of the construction, you mentioned design constraints that you would want to find the graph pH values with.
So, but what mean you exactly? It's a pipeline stage?
Mm-hmm. Yeah.
So, here.
Yeah.
And what do you mean?
Somewhere you said that if an edge violated a number of design constraints,
Yeah.
if it violated those constraints, you could remove it.
What were they? What was its constraints?
So here it was here. It was it.
Okay.
Yeah. So you just waited, and then so you can compute the MST, and then there's less violation. Yes, and so with this design option you can add so to get a better playable level height. Yeah.
So I think the question is like, what kinds of things can the user ask to to be changed or constrained about the graph? So I think, for instance, you could. I remember reading the paper. You could constrain things like the number of connections, this kind of thing, right, in the graph, and then at that stage it would make sure those were all fulfilled, or.
Yeah.
I'm just thinking maybe a practical example. You said you inserted the arena in that level. Maybe you had some constraints about how many exits and entrances it would have. What would that be an example?
So, yeah.
So that massive arena in the example at the end, that was like a special case, right?
Okay. So this example, so this is a special case. Yes. So, yeah, we have generated 6 separated level graphs and merged them in the last stage together. Yeah.
And they're like designed so that like they have particular connections.
So this is more detailed in the paper. Okay. So this is not so easy. So you can fix rooms and then these were connected and so on. Yeah.
Maybe one more quick question while Ahmed, you want to plug yourself in. You have one more question?
On one slide, you listed the computer specs with the graphics card. Are you using GPU for this or just CPU?
Just CPU, yeah.
It's a really fun paper to read. I really recommend it. I think we should thank Simon. Okay. All right. Next up, we have Taksim, presented by Ahmed. Are you up for that? Yeah. Good to go? All right. Take it away.
Question. Yeah. Hello everyone, this is Ahmed Abuzuraiq from School of Interactive Arts and Technology in Simon Fraser University, Canada. This work is a collaboration with Arron, Ferguson and Philippe Pasquier from the Media Creation Lab. So the title is a bit different from the one you're reading. So it's a concept graph partitioning framework for generation of game spaces using assisted programming. Introducing a new technique here. And the presentation will be trying to explore the potentials of this technique, limitations, and how it's situated within the literature and the practice. So it's more of a kind of exploration paper. So I think a good entry would be to ask the question of what is the design. So I'm going to take this as a kind of a starting point toward introducing the approach. And one possible definition coming from artificial design is that it's a design of a form that has a function. It's a very general definition. This room, for example, have a specific depth, width, and height, so that it serves a specific function, which is that being a presentation room, basically. In games, forms are the game spaces. We can have platforms in a platform level. We could have rooms in a dungeon or the walls of a cave, or just the open regions in an open adventure game. And all these forms would serve an in-game function, like allowing the player to walk in them, fight, or talk. And they can also support the immersion of the game, or just tell a story about the world of the game. We can expect the forms to vary based on the function they serve. So I'll take another specific example to explore these two concepts. And it comes from an analysis by Joris Stormans, where he analyzed the game in a level in the game, The Legend of Zelda. So he found that by analyzing this level, he found that we can describe a level by two structures. The first is the game space, that's the one on the right. And it's basically the spatial structures and the geometrical representation of the level. And on the left is the mission graph, which is a directed sequence of tasks that the player is expected to accomplish in that space. So the missions would start with a start node at the bottom, and then there will be tasks like defeat a monster, solve a puzzle, and then eventually at the end it will ask him to defeat the boss and then reach to the end location. These tasks in the mission graph and the regions in the space are often mapped in a one-to-one manner, so one region would be reserved for a specific task, but it can also happen that for one space there are multiple missions, so the player will be revisiting the same space to accomplish different missions. Now, when designing by hand, a designer will alternate between these two concepts mentally, but without explicitly representing the missions. So be thinking about what the player will be doing while they are drawing or sketching. But when automatically generating these game levels, as Dominik argued, it helps to split these two structures and treat them individually and generate each one of them in a different way. Now, this allows us to find the question that we're trying to answer is that how do we generate game spaces on the right that accommodates or can give rise to an intended mission graph? But scouting in the literature and the practice, we found that there are generally two approaches to that. The first starts by generating the game basis and then leaves the mission graph as an emergent property. And the second specifies the mission graph and then translates that into a playable game space. These are examples of the first. So in this case, the rooms are generated. And then the connections between the rooms are assigned randomly. So we have little control over how will these rooms be connected. So if I have a specific kind of constraint that the player should start somewhere and then should solve the puzzle somewhere, I cannot really make sure that this sequence of tasks can actually be mapped to the space because I have no control over the mission graph. The top-down approach, though, more frequently seen in the literature, start with the mission graph and translate that into a game space. And one of the earliest is Dominant, where they start, or after the creation of the mission graph, the translation is happening by using shape grammars. I won't be able to go over the details, but generally we have the first would be shape grammars. You can see that the adjacency between the two rooms is represented by the absence of a wall. In the second approach, you have graph drawing or embedding. So the actual graph will be embedded in, for example, a two-dimensional grid. And then when each node is in a single cell, you just replace these cells with rooms. And if there is a connection between the rooms, you add a corridor, for example, in the bottom approach, in the middle. And the third one, we start with the mission graph and a set of templates, and we try to find a combination of these templates that satisfies the mission graph. We believe that our approach is somehow in the middle. It's a meat in the middle, not meat in the middle. So we start with an underlying a structure, a subtract, we partition that in such a way that it creates a top-down mission graph. It satisfies the mission graph. Give an example here. So we have this very simple mission graph, just 3 tasks that the player is expected to accomplish. We'll have an underlying structure. In this case, it's a 3 by 3 grid. It could be any other thing. I'll give examples of what can you put in that side. Through the underlying structure, we extract a graph, we call it the basic graph, that describes the adjacency between the cells in the structure. And then finally, we partition this graph such that the adjacencies between the partitions matches that of the mission graph. So for example, the yellow partition here and the red partition are adjacent, but not the yellow and the blue. By doing that, by partitioning the basic graph, we end up partitioning the underlying structure as well. And these are different variations of the same mission graph, the same underlying structure, but different partitions. Now, we can also allow removing nodes from the basic graph. And when we allow that, we get a larger variety of solutions. And throughout the representation, like the removal of nodes will be represented by white color. So node removal allows for create larger variations, but also it will allow us to work with mission graphs that have cycles in them. So for example, I'm using now a large underlying structure and a different mission graph, and this cycle in here can be seen on the right, and the node removal, the white spot in there, allowed us to create this cycle basically. Now, one advantage of starting with an underlying structure is that we can capitalize on the rich examples from the practice. This one is from polygonal map generation by Ahmed, where the generation of a world map starts with a Voronoi diagram, and through some forms of annotations and transformations, we eventually get a map like that. So that's an island, and the colors show you tells you something about the terrain. So a system can take either of these, can take the Voronoi diagram or the transformed version of it. And we can, for the same mission graph from before, we can generate levels that map that mission graph into the Voronoi diagram, or only the interior of the island. The removal of nodes in the island, for example, could be interpreted as mountains or just impassable regions. You can also see how the removal of nodes created some kind of structure in the second example, or just was the pivot point around which everything was revolving. This is another example from the practice. It's not generated by the system, but it's perfectly possible to do so. This is Asgard's fantasy map generator, and I'm just mapping that mission graph into the same space. Now, this could be interpreted as an open world level where you are moving in a kind of a forest, for example, or on an island, but it could also be seen as a continent with political maps. So it's more of a game of chess, for example. Now, you might have noticed that I've not been committing a specific type of game spaces. That's because I'm kind of exploring this idea, but we can see, for example, when the underlying structure is like grid, we can get something like more of that looks like rooms. When they are more Voronoi diagram and they look more organic, we get something that looks like a cave system. When it's done in an island, then we can have something like an open world island or a political map. And it really depends on how you interpret the mission graph and what's your underlying structure. Now, the approach we took to partition the underlying structure uses unstructured programming. I won't go into much detail in this, but generally speaking, unstructured programming is a declarative logic programming paradigm. You describe your set of facts and constraints about them, and the result will be a set of facts that satisfies these constraints. We were motivated by the argument made by Smith and Matthias for using unstructured programming in content generation, and I'm quoting them here. Unstructured programming, provides an explicit description of the design space, and by concisely capturing a design space as an unstructured program, we can rapidly define and explicitly sculpt new generators for a variety of content domains. did help us in implementing the system. That was actually the case for us, because the same system was developed previously in a different technology. Like I was using A-star and moving into consumer satisfaction, I found that it was indeed so. But also, when extending the system by developers in the future, I felt like they would benefit from assisted programming. Now, I won't go into the actual details of the assisted programming statements, the actual code that I implemented, that it's fully detailed in the paper. What I will do now is give a kind of a system view of Taksim. On the top level is the application level. It could be the actual in-game system or a user interface that the designer is using. The first part of it is where you provide the underlying structure and the basic graph, which could be generated like this, but it could also be manually designed. So the designer might be drawing the actual level by hand, and as long as it has a graph structure, then Taksim can still work with it. The second is like you provide the mission graphs, which could be generated or again manually created. The third part are more additional constraints that you want to add to further control the result. I will list some of these constraints now. The first is a mapping constraint. So something you can say is, I want that particular region in the island to be the start region. And because the underlying structure is there from the beginning, you can say, I want that region to be mapped to the start. And you can control the number of nodes or cells. You can say that I want at least 4, for example, in the post in the partition representing the post level, post region. You can, assisted programming solvers also have the ability to optimize certain quantities. You can first count the number of links between the partitions. So like these are the number of cells that are between partitions. So maybe you want to minimize that so that you have only one gate, one place to connect in the two rooms, and you can minimize that. And finally, you can also control the shape of the partition by controlling what's called the internal graph of each partition. So, for example, this partition has a graph that is a cycle of 4. That's the internal graph of it. But and we generated this particular level by saying, okay, I want the POS, the region, the partition that represents the POS mission to be of this shape, to be a square, to be a cycle of 4, and this way you can control its shape. And finally, when we have all this data, we have the underlying structure that's translated into a basic graph. We have the mission graph, the additional constraints. All of these are translated into a syntax that the assisted programming solver expects. In addition to that, in addition to these statements, we also pass a randomization seed. They will get the results as a list of statements, and then we parse basically the result using these list of statements. So that's basically how it's going to be used. You'll get this list of statements, and then you will be doing something with it in game. Like you will be told that node 1 should belong to the partition, the yellow partition, and so that's you. In this case, we are just coloring it, but in actual game, you will start getting the geometry, detailing that particular level, and creating walls and so on. So there are a couple of advantages for the approach we're taking. The first is that there's a separation of concerns. The geometry, the aesthetics comes from the underlying structure, and the design intent is expressed as the mission graph. We have access to the underlying structure from the beginning, so we can express constraints in terms of elements in the underlying structure. And then there are diverse sorts of variations. These are different modes, so we can start with a fixed mission graph, a fixed underlying structure, but then we vary the random seed to get different results. Or we have one mission graph, but the underlying structure, like for example, islands are being generated, but with one random seed. Or we have one structure, like maybe possibly manually created, so we can't really have control over it. And one random seed, but we are varying the mission graph. So that's speculation. Why would you need to create multiple mission graphs? For political numbers, it might make sense, but yeah. And then finally, we can have a combination of all of these. I'll go quickly over limitations. Currently, we are still understanding the relationship between the underlying structure and the machine graph. Because, for example, this basic underlying structure currently only support this machine graph. It's just for cells, and it won't be able to support it. But this is where the concept of reuse of space comes. Currently, we are not using space. We are actually having a one-to-one mapping between the nodes in the machine graph and the space. So that's how the system currently works. And we hope that in the future, possibly by introducing a middle structure in the middle, like the space graph, we can first map the machine graph into that and then generate the level. And finally, in 1 minute, good timing, ASP is hard. We don't expect the designers to be expressing these constraints by actually writing the code. So what we expect to do in the future is, currently we have a Java client that takes constraints written in code and translate them into untested program statements. But eventually we can have a mixed initiative interface where the constraints are really expressed in a visual and interactive way, and that is then translated into machines. I think that's all. I've covered what machine graphs and the spaces are, how are we situated within the literature and the practice, an overview of the system, and finally the conceptual arguments for its advantages and some limitations. That's all. Thank you very much.
Fantastic talk, exciting stuff. Do we have any questions?
I have more comments. I really like the constraint system that they put in place for mapping and constrain how the map will look. These companies, the way they are using this type of information, the constraints are much more elaborate because the procedural generation system starts looking to the fauna and the flora that's going to be placed, etc. The environment, if it's going to be, depending on the height, it's going to be snow, etc. We mapping the textures. So I would strongly recommend that constraint system would be a bit more generic and just accept constraint, and then how that constraint would go forward will be a bit more defined in the future, or just have a setting of rules that you can define afterwards what that will be.
It is possible to do this. The problem is not in whether it's possible to use these additional data in this case, for example, because you have the underlying structure, for each cell you know, for example, what kind of terrain it has. You can generate all kind of game-specific data for each one of these cells, and then when you express the constraints, you can say, okay, I want you to put the puzzle in the place that have this much forest or this much whatever. So you can do that. The challenge is not usually, because it's a formal system, it's in going from your descriptions that are requirements in your mind.
How you formalize that to the system?
Yeah, so what I'm imagining it is when you have a mixed initiative tool where you express that visually, then it becomes easier to actually translate that requirement. Okay?
I would consider a language.
So,
specification language.
Okay. So a high level specification language.
No, we can talk about that. Sorry, I'm taking too much.
But that's it, one. Yeah.
It's great, ASP tools always get people in this kind of mood, I find. Ahmed, do you want to come and set up, and maybe we can take it, someone got another quick comment, question?
I guess, so some of the things in the Zelda examples, you've got stuff like graphs, I've got stuff like jumps, and a jump, require you to go across a space, so then you're now creating something where there would be other constraints in your graph and the mechanic of the power. Where you said, maybe we'll add a loop back through. You can't really add a loop through a space that's a kind of void space by design, so you can jump over it. So I think there's kind of sometimes some more ties in the mechanics that dictate more about the space that you can currently express, especially with outputs.
Currently what I have is, so it rests on the assumption that any two regions where the player will be doing things in a sequence are also adjacent in the space. And it's kind of,
I suppose some of them I suppose they're just different fidelities in which you're kind of operating just some of the actions within some of the Zelda examples.
So can that be the same machine graph but more detailed?
Possibly. Yeah, or more relationships with the space expressed.
Yeah.
All right. Again, recommend the paper, lovely diagrams. Our set program is always fascinating. You check it out. Let's thank Ahmed one more time. And now, up next.
Okay. Hello everyone. I'm Ahmed Khalifa, and I'm going to talk about a game I created called ELIMINATION. And this paper is about the design behind it and the analysis we did after we collected a couple of data from players. So just to explain, so ELIMINATION is a simple word game where you try to eliminate multiple letters in front of you, so the remaining letters make a proper English word. For example, if this is a challenge you have in front of you and you want to find the word hate in it, so you can press on the letter D and remove it, and then you can press on the letter L and remove it, so you get the word hate, and you get a score for that. So this work we will talk about kind of like a post-mortem. So we'll talk about the game design, all the decisions we took during designing the game, and the level generation systems that we use, and some of the analysis that Dan Gopstein did on the player data we have. So from the game design point, the game first have 30 levels. All of them are procedure generated and curated. The only thing I did is I just tuned the parameters for generated for each of these levels, and then let it generate for it. Each level have 10 challenges, like the one I just explained, and if they finish all the 10 challenges, they pass the level. But to make it more intriguing, there is a timer. So if the timer runs out at any time, you lose that level. But also, if you lose a level, you still can continue the game. You don't need to stuck in the level. We open the next level for you, so you don't need to repeat the same level if you don't want to. So one of the things we decided at the beginning is how we could influence the players to choose certain words or to choose something. So the first thing is through using the score in the game. So we made the score of the game to be relative to the length of the word. So people tend to pick longer words. For example, if this is a challenge and this is a couple of words inside it, people will most likely, if they want to get higher score, will pick hate. Also, another way is we use something that called the 2x, which one of the letters might have a 2x symbol on top, which means the score of that. Any words that have this letter will be double. So by this way, if you have multiple stuff that has the same length, it will make you try to find the one that has the 2x in it. For example, here it will be true. So after that, we start on the generation. That was the guidelines we wanted to do. So we use feasible and feasible to population genetic algorithm. So for people who don't know it, it's genetic algorithm has two populations. One of them is trying to satisfy a certain constraint, while the other one is trying to increase the fitness of the whole population as a whole. So the generation technique, that's what it tries to do. It takes in a couple of words from the dictionary and try to mix it in an intelligent way such that the output word still has the two input words in them. For example, car and cool. The car rule down there, you can find the cool in it and car in it, and you can get them in the game. So the representation to satisfy that is we use just a list of integer. The first couple of integers were just pointing in a portion of the dictionary what are the words are selecting in the mixing. Then after that, the rest of the integers just tell you from which one you're gonna pick, from which word the letter you're gonna take. For example, in this case, let's say once it will take C from cat, and then another one which means the A, and then two to mean the C from CoG, and it goes on until it gets all of it. But we don't stop here because, as you can see, CoG have redundancy in it. So we use a greedy algorithm that just remove letters that unnecessary, such as the C in the middle. If you remove it, you still have the word cat and CoG. You can still get them in the end. So after doing that, that's the presentation. We have the constraint which was a simple constraint because since the game should run in the browsers and on tablets, and we don't want the letters to be small and tiny if you have 10 letters on the screen. So our constraint is always to have as small much of letters to compress the mixture as much as possible. So we use a target length. So for example, if the target length is 5, and these are two different chromosomes, The first one will be in the invisible population because it's things that comes out of it, which is Karul is 6 letters, while the other one is 5, so it will be in the visible population. For our fitness function, it was more like a challenge because we wanted to try to control the difficulty of the level a little bit. So it consists of 2 parts. The first one, it tries to make like words that are like after each other more apparent. Like for example, we define something called the max sequence. Let's say the max sequence is 3. So this means any word that's 3 or less letters, it tries to find as much in the actual challenge words that are after each other. So for example here, the word hat is after each other, H and AT after each other, and the word del is after each other, DEL in the challenge word. So the fitness of this portion will be 2/6 because there is only 6 words, so you get 0.33. And the second part is try to make it a little bit more difficult by trying to get anything that's more than the max sequence. So for example, in the hat del, the only 2 4-letter words or more are hate and hate. And both of them are not consecutive. Like the word hate, the E is separated by the D, and the word hate is separated by the T in the middle. So your fitness in that case will be 1, and both of them are just averaged in both cases. And the last thing in the generation is after it done and got the output, it try to get the 2x letters. So we could have just picked the rarest letter in the word, but we found that it's always going to be very bizarre letters. So we wanted to be more variable and some randomness in it. So what we did is we got the source words, and then we got the least common letter in them, and then we pick one of them at random. So from car, C is the least common used English letter in these letters, and L, and then selecting one at random, it will be the L in the end. So we ran this game in January, launched it in January, and then later we looked in, I think after 98 days, we looked at the data. We got like around 975 playthroughs. Each playthrough is a complete full level, which means 10 challenges. So it's like an aggregated of 10 challenges. These are a couple of statistics, such as most of the players they played on average 20 challenges, which is 2 levels only, and then they left the game. And the highest player played with around 2,000 levels with 2,000 challenges, which is since there are 30 levels and each one is 10, this means they replayed some of the levels multiple times to get higher score and try to achieve better score in that levels. So one of the things we were trying to do is we tried to have difficulty when I was trying to tune the parameters for the generator. I was trying to make the difficulty as a sawtooth difficulty. So because I didn't want the difficulties always increasing in the game, so people get bored by it getting harder and harder. So I wanted every 5 levels the difficulty drops dramatically, so it became easy and they get some breathing time, and then it starts increasing again. So we did a linear regression for that. And it's kind of sawtooth-ish at the beginning, and then in the end it gets noise and awful. But we think the awful part in the end, also because we have less data near the end, if you notice from the previous graph. And so it was interesting to just see that if you have more data, it could be better, but maybe the parameters didn't work well. Another thing, we wanted to understand how humans selected the words themselves. So we tried to predict the selection rate based on some of the parameters, such as if the words you select have a 2x in it, or how long is the word you selected, or is the word a dirty word by Google definition, which at the beginning we had a hypothesis about it, dirty words selected more common, but it was not true. Is the maximum sequence of letter also is affecting? And when we did all that in the linear regression, we only found that the word length and the max sequence letters are the more effective. And max sequence letter was very clear, because if you saw hat after each other, HAT is the letters, even in the middle of all other letters, you can notice it right away and pick it. But word length, although we wanted it to be selected, but there was some tricky stuff that happens. For example, people selected because longer means higher score, so they selected. Also, VZ people like try to find the longest one so they don't press much. Then he tested the game for me. He did this all the time. He was like, I need to select the least amount. Selected by accident, maybe you were removing a letter and suddenly the remaining letters made a word that is there. And there's some cases that's impossible to find the short word. For example, if you're trying to find the word far here, if you try to remove the A, it will be a fart, which is a word. And if you try to remove the T, it will be a fart, which is still a word recognized. And you can never get the word fart. So it's contributing from all these. So from all that, we just found out that we need to a little bit to try to do some auto-tuning to our generator and the parameters to be auto-tuned so we can have better like sawtooth difficulty curve. Also use some accurate models because we never use any human models when we are generating. We just generate based on my intuition, what people would like and what they won't like. But since now we have more data, we can have better and accurate models for the players. Also maybe level to be a little bit more diverse from each other because right now there is nothing about the content of the word. Maybe some levels be composed of dirty words only, or some levels have composed of different types of words or like always longer words or stuff like that, but we didn't care about this part, so it would be interesting to try that. Yeah, thank you.
Thanks very much. We've got a few minutes for questions. Any questions?
You can tend to would be neologism by a portmanteau, which is something that happens in context creativity. And one of the things they've done there is check the linguistic properties of the generated word. All the words you put on screen can be pronounced.
Yeah.
Were there any which couldn't be pronounced? It might add to the benefit of the game if you can actually pronounce the word.
We didn't check that, but there was couples that couldn't be pronounced because when it makes it just put like a lot of consonants after each other and then the vowels in the end, so it's just very hard to pronounce. But we never like during generation or like try to consider that it might be a good idea to try it.
There's things like the same pronunciation dictionary you need to check it.
No, I will look up for that.
I have a question about, you mentioned you wanted a sawtooth difficulty.
Yes.
But you talked about fitness, and were those two the same? Or
so this is saying, I like pass it quickly, so the fitness does not care about the difficulty, but the parameters I choose for the generator at the beginning, the input parameters, I control them in a way that they reflect the difficulty, which is such as the maximum sequence. Okay. So I want, when you're generating, 4-letter words to be consecutive, which means it's easier to spot, so it became less difficult. So I controlled that. This is the only part I controlled by hand. So that's why the fitness didn't care much about it, but yeah.
So it's not one dimension that is like...
It's like, yeah, it was like multiple, like 7 or 8 parameters I used. So.
Okay, do we have our next speaker ready to set up? Okay, fantastic. And then is there a question in the back?
Very nice question. Yeah. Why did you use physical and physical? And did you compare with some other algorithm to see what it brought specifically?
Okay, so I used physical and invisible because I had the code ready and I was kind of lazy. So that's the first thing I can say. Second thing, yeah, later I had other algorithms I wanted to try, but I already launched the game, and then later Julian was like, oh, that's an interesting game, and we have a lot of data. Let's try to do some analysis. So we didn't have time to try the rest. Sorry about that.
Very honest research, I like it.
I appreciate that.
Those are quick.
Yeah, quickly, what prevented you from making in-game procedural generation and creating an infinite mode?
There is in-game procedural generation also, so someone playing it in the back. So there is daily mode, there is infinite mode, and there is also the levels. So I had a talk a long time ago with a developer for a game called Line. It's a very famous puzzle game on the phone. and they also have set of levels, and they have a daily mode, which is generate on the fly on the phone. And when I asked why you have set of levels, and he told me he did tons of tests, and he found out if you don't have sets of levels, people get bored super quickly, or play it just for relaxation. But when you have set of levels, some people get this feeling they need to finish the levels and finish everything in them. So I did all possible ones, like, here is an infinite mode that generates on the fly. Here is a daily mode where it generates once a daily, and you can see your friends with the same stuff. And here is some like group of levels that you can just like play and see if you can finish all of them and be like 100% achiever and all that stuff.
Well, I haven't managed to finish this session, so I think we should thank Ahmed for a great talk. It's another very fun paper where, in Ahmed's case, you get this vibe of like the research and the game design aspects kind of playing off each other very nicely. With a bit of projector luck,
I believe.
Maybe we need to. Are you on a different source?
I can do. Is there an HDMI?
There is. That's way better.
Thank you.
Can you, Joshua?
Yes.
Up next, our final talk for the session.
Perfect.
One second.
It does this sometimes. I'm not sure why. I really wish that hadn't happened. Does anyone else read Wait But Why?
Yes.
Nice. Yeah, that's good.
Right. I think we're getting that.
Okay, but sorry, I don't know why it's not mirroring.
So the signs I'll hold up are based on a 13-minute thing, so don't panic. There's like some questions and stuff like that.
I think it's going to work. Yeah, it's going to work.
Right. We got that. All right.
Okay.
Take it away, Josh.
Hi everyone, my name is Josh. I'm from the University of Alberta, and today I'll be presenting on my paper towards procedurally generated languages for non-playable characters in video games. So this work was done with my supervisors, Vadim and Matt Brown, and also with my colleague, Sergio Hernandez. So the primary thing that we're addressing today is communication between ambient NPCs. So ideally, we would like these languages to be grounded. So right now, typical ambient NPC languages are pre-scripted, whereas if we could actually ground these languages in the environment which the NPCs are playing in, or are existing in, then we think that this could make these languages more responsive to changes in the environment. They could react to unexpected player behavior, and also they could lead to unexpected, interesting behaviors. So the specific problem that we're addressing is the generation of deep neural networks, which can create their own grounded languages from scratch, and can use these languages to actually cooperate with each other. So we need an environment or task for a grounded language to emerge, and so the one that we'll be using is called a repeated referential game, which I'm going to present on the next slide. So we chose a repeated referential game because it's an extremely simple environment. It's easy to detect whether or not communication is occurring, and also to analyze what the language that emerged, what the words actually mean. And also previous work has shown that a repeated referential game is sufficient for interesting, complex languages which actually exhibit natural language properties to emerge. So this is the actual referential game that our agents are playing. And so a referential game is between two agents, a speaker and the listener. And what we do is we show the speaker some concept, which in this case, which we call the target. And we show the listener the target as well as some distractors. And given just having seen the target, the speaker has to produce a message which the listener uses to ideally choose the target out from the distractors. So there's some important related work here. So first and foremost, previous work by Lazard, Rymon, and Clark actually did train deep neural networks to play a repeated referential game. The key difference between
between their approach and ours is that they used a gradient-based deep reinforcement learning approach, whereas we're going to be using a gradient-free evolution. And the inspiration for that gradient-free evolution actually came from these two papers by Such and Rawal and Mikulainen. In the case of Such, they used a genetic algorithm to train deep neural networks to play Atari, to learn the Mujoko humanoid locomotion task. And also Rawal and Mikulainen showed that it can be beneficial not just to use a fixed handcrafted deep neural network architecture, but to actually evolve these architectures from scratch. So we're going to be, like I said, we're going to be evolving the weights and architectures of agents which will learn to play a repeated referential game, and we'll be using gradient-free evolution to do this. And we think that a gradient-free approach in this case is particularly beneficial for real-life applications like video games, because these algorithms have been shown to train very quickly, with speed-ups often 10 to 20 times that which is seen with reinforcement learning. They're easy to parallelize, and also since you are not computing any gradients, there's no backpropagation, and so there's actually no need for GPUs. So we'll be simultaneously evolving pairs of speakers and listeners, and we'll take these speaker-listener pairs, evaluate their performance at a referential game, and it's a standard genetic algorithm. High-performing agent pairs will be chosen to reproduce. So the actual agents that are playing these games are recurrent neural networks. And so that we can evolve the architectures of the agents, we're implementing them as what's called a program tree. And so a program tree consists of inputs, which are the blue circles here, as well as operators. So there are binary operators like add and multiply, and then unary operators like tanh, sigmoid, relu. And since we're evolving architectures, for the first generation, we need an initial architecture that agents are initialized to. And we experimented with two different initial architectures. The first is a gated recurrent unit, so just a well-known LSTM variant. And the second at the top there is actually we're just calling it random initialization. We defined this small tree, and any of these agents, their initial architecture is this, has the same structure as this small tree, but with the order of inputs randomized, the operators randomized, and yeah. So to actually evolve our agents, when evolving the weights, we're just using so when agents reproduce, we just add random Gaussian noise independently to all of their weights. But to evolve the actual architectures, we defined 5 different architectural mutation operations. And so there are 2. So the first 2 operations are binary insertion and removal. So this is an example of binary insertion. We chose a node, and we inserted a binary operator as the new parent of that node, and then selected a random input as the second child of the binary operator. And then in the other direction, when we remove a binary operator, we just randomly replace it with one of its 2 inputs. And then we have two similar operations for unary operators. In this case, you can see we just chose this node, and we chose a random unary operator as the new parent of the node. And then in the other direction, it's just removing that unary operator and replacing it with its child. And then we didn't show the 5th operation here, swapping, but this is essentially just swapping an add node for a multiply node, or a tanh node for a relu node. So this one doesn't change the size of the tree at all, it just switches an operator. And some details about the actual evolution. We used a population size of 1,000 agent pairs. So this is 1,000 speakers communicating with 1,000 listeners. Evolution proceeded over 420 generations, and we allowed the agents to pass messages of maximum length 2 with a vocabulary size of 60. So this gave 3,660 messages that could possibly be generated. And so to actually evaluate our agents, they needed something to communicate about, and so the data set that we used was called the Visual Attributes for Concepts dataset. And what it consists of is 463 concepts, like dog, sailboat, hammer, and each concept has a number of human-generated annotations. So you can see here the sailboat concept has annotations, has deck, has sails, is large, is long. And we separated this into training set and a test set. So the actual evolution, so when agents learned their languages, they learned on the training set. And then when we finally evaluated the performance of the agents, we did it on 8,000 samples from the test set. So this is important because this means that when agents were evaluated, it was it was referring to objects that they'd never seen before. And the reason that we did this was to make sure that the language is actually generalized. So they'll need to have some level of structure so that they can actually, when they see brand new objects, can communicate about them. It's ensuring that they're not just randomly assigning messages in a somewhat meaningless way to different concepts. So we tested 4 different experimental configurations. So like I said, we had this random and this gated recurrent unit initial architecture, and for each one we tested them with and without architectural evolution. So in these 2 groups, this RT and GRU, those were just the random and gated recurrent unit initial architectures, and we only evolved the weights. There were no changes to architecture, but this plus E implies that we actually evolved the architectures in these cases. We used 4 distracting objects. So baseline performance would be 20%, and each of these ran for a single day on 36 CPUs, so 36 CPU days per evolution. And what we saw was that in the case where a gated recurrent unit was used as the initial architecture, there was actually very little benefit from evolution, if any. But what we were glad to see was that the random initialization actually was completely incapable of learning the task. As you can see, it performed at about baseline chance. But when we added architectural evolution to this random RNN, it actually performed comparably to a well-known LSTM variant. So we were glad to see that performance was well above the baseline at a bare minimum. But the results were still significantly worse than what was previously achieved with reinforcement learning. We saw a drop of about 30% in the final success rate of tested agents. We were glad to see, though, that with this RT plus E group, so the random RNN with evolution, that this agent was able to learn languages without any specific engineering beforehand. Weights were randomized. The network architecture was randomized. And also the languages themselves, like I said, we evaluated them on a test set to ensure that the languages actually had structure. This would also be called compositionality. And we were glad to see that this was the case. So this is a selection of messages and what those messages refer to for a high-performing agent. And you can see that there was this grouping. Messages which started with 10, with some unusual exceptions, referred entirely to birds. Messages which started with 28 referred to vehicles. Messages which started with 53 referred to 4-legged animals. So there were clearly some structured languages emerging from this. So for future work, one of the most obvious things is that we would like to improve the performance of this approach. One problem we think is that the architectural evolution that we used was extremely simple. But since we started working on this project, there's been some really amazing work on actually evolving the architecture of neural networks. And so we'd like to use a more interesting algorithm. Right now, interactions only between NPCs. But we think it would be really interesting if eventually this could be something where a human can actually engage with an NPC. One problem with that is that to develop these languages from scratch, our agents had to pass millions and millions of messages back and forth, which isn't a particularly stimulating activity for a human being. And so what we think we could actually do is use human proxies. So train neural networks to be able to emulate the way in which a human being would interact with these agents, and train the agents to communicate with the proxy and see if that communication actually works when it's communicating with a human instead. And like I said, we used a referential game, which was simple, and it was a good start, but we'd really like to bring this into some more interesting environments, like an artificial life environment, or, since we're at a game conference, an actual game. Yeah, that's it.
Fantastic stuff. The language stuff is absolutely brilliant, and really lots of this new stuff. Do we have questions?
For observation, if you wanted to entertain a learning system where humans were involved, you don't have to do many iterations. You can use a very large number of humans, so you can get into the right kind of game. you could make a kind of consensual language.
That's a great point. Would the humans need to be coordinated with each other though? Because otherwise they could all be. Okay.
Yeah, you get up to an MMO and look at the chat channels. There's plenty of
yeah.
or even the game within Discord or something like that.
That's a great point. That's what my lab would really like to move towards, is bringing humans into this, and so that makes a lot of sense. Thank you. Hi.
Hi. It seems, computationally speaking, quite expensive to do this. So I'm wondering, could you give me an example of when you would choose this over, let's say, more naive methods of generating a fictional language?
Trying to think. So how would you? So the thing here is that I think the reason this was computationally expensive is because the languages that emerged were actually they were grounded in their environment, and I'm not sure how you would achieve that without this potentially longer training time, unless you were actually to go in and individually link messages to different concepts and different behaviors that you could see. But then that sort of brings it back to the same problem that I mentioned initially, where I think the point that we're sort of going towards here is that you don't have to make those connections by hand. You don't have to. So
yeah, so it's the trade-off annotation by humans, or
yeah, I'm absolutely going to be the first one to admit that right now you probably wouldn't use this. So I don't know if there's a situation right now, but I think that as these techniques actually develop and as the languages become more interesting for an actual game, then yeah.
Right. I think it's time for the universal language of coffee. So thank you very much.
Thank you.